A very good day to everyone. My name is Jia Sen. Today I'm going to share about my FYP proposal defense with the title of Modified PID Controller for Improved Control Loop Performance under Stiction's Nonlinearity. In today's sharing, it will cover introductions with the problem statements and the background study, literature review, methodology, and conclusion. Without further ado, let's move into the main topic today. Firstly, we will start with the objective. My FYP basically will mainly cover two objectives, which are comparing the performance and robustness of recent PID compensation methods and further modify and improve it. Before starting off to move into the recent compensation methods, let's discuss about the problem that we face and some background of studies. The presence of control valve nonlinearities like stictions, backlash, and deathband is a major cause of oscillations in the control loops. Among the most types of nonlinearities in control valve, stictions is the most common and one of the long-standing problems in the process industry. The presence of oscillations in the control loop increases the variability of the process variables, thus causing inferior quality products, larger rejection rates, increased energy consumptions, reduced average throughput, and decreased profitability. There are some proposed solutions in order to solve the valve stictions issues. The best solution is to run the maintenance and repair on valve, but it is only possible for long periods. Hence, the changes on traditional algorithm and structures of PID or compensations method have been introduced to reduce the occurrence of stictions until the next maintenance. Among the PID-based compensation methods, we can separate them into three different types, which are retuning PID, modified PID, and augmented PID. PID controller retuning used in the process control loop is able to significantly reduce the amplitude and frequency of oscillation by tuning or finding the most optimum parameter for the controller setting. Newton-Raphson methods is one of the solutions to apply in the retuning of controller to improve the performance of stiction compensations. Next, the second existing PID-based compensation methods is modifying the traditional PID algorithm without adding an extra compensator. The points listed below the modified PID are the methods that have been found. Modifying the PID controller without using any additional components would be a good option for the industry to solve the non-linearities problem on behalf of valve stictions, because it can reduce the overall maintenance cost. Lastly, adding the compensator block to the PID controller, also known as augmented PID, will be another approach of the PID-based compensation method. This method will be our main focus today, since it can guarantee the disturbance rejections and setpoint tracking in the control loop and remove the impact from the sticky valve. There are 8 different types methods, and the comparison will be made among them. It comes to the literature review. Before doing the comparisons of those 8 augmented PID methods, we need to understand what is stictions and how can we quantify it. Previously, several studies have been carried out to define and detect stictions. However, those studies have less descriptions in terms of the static frictions or stictions mechanism. Thus, Charlie et al. Has proposed a new definition of stictions by focusing on the input-output behavior in the control valve. Forces that are present inside the control valve include the air pressures that come from the air inlet, the elastic force provided by the spring, and the frictional force between the stuffing box and the valve stem. The positions of the valve stem is determined by the balance between these three forces. The static force or stictions occurs when the valve stem movement is under the static phase. 4 important elements have consisted in the plot, which are the deathband, stickband, slip jump, and the moving phase. According to the graph, point A to B indicates a deathband and continue from B to C, which indicates as the stick band. The valve remains stuck due to high static frictions than the dynamic frictions. The valve enables to continue moving once the controller output overcomes the static frictions, where the slip jump occurs from point C to D. This is because the potential energy stored due to the high static frictions is abruptly released by converting into kinetic energy. After passing through the path of slip jump, the valve stem continues moving, and it has been indicated as the moving phase from point D to point E. The valve stem that continues moving under the moving phase may be stuck again at point E when it changes the directions, and the whole process will be repeated. It comes to our main discussion today, which is the augmented PID methods. Among the augmented PID proposal, knocker method approached by Haslinda are the first method that is invented by adding the compensator to the control loop. The short pulse will be sensed from the compensator to move the valve from its start positions. This method shows a good result in the reductions of oscillations and fast motions of the valve. However, it may create excessive movement of the valve and thus reduce the lifespan of the valve. In 2008, the two-move method has been proposed by adding two compensating movements to control the output in order to make the control valve arrive to the desired steady-state position. Nevertheless, this method required to quantify the exact amount of stictions and thus is not feasible in the industrial applications. In the coming year, a constant reinforcement method, also known as CR methods, has modified the knocker methods by adding constant quantity of the compensating signal to the controller output instead of the short pulse, but unfortunately it still cannot solve the excessive movement very well. Therefore, the improved knocker method has been proposed by changing the pulse to sine signal. It can perform better than the knocker method by reducing the oscillations of output signal and rejecting the disturbances satisfactorily. However, it's still facing the same problem like knocker methods where it can't reduce the aggressiveness of the valve stem movement. In addition, a model-free Stiction compensation method has been proposed by Arifin et al. By using a compensating signal, which is a function of control error, but it requires a lot of specific parameters and all will be different for different processors. Recently, foremost method has been suggested by taking two-move methods as the foundations and modifying it with 4 open-loop movements. This method will be further discussed later, even though it performs poorly if the Stictions amount can't be predicted accurately. Also, the variable amplitude pulse method will be further explained in the next sections. This method is aiding the pulse with varying amplitude to the controller output in order to minimize the error. However, there will be a limitation on these methods if both IE and valve travel exist where the optimum pulse amplitude can't be obtained. Lastly, it comes to the novel Stiction compensation methods. These methods will add the pulse only for short durations to move the valve from its start positions without creating any aggressive valve movement. We will explain in more details in the coming sections. All compensators exhibit good capability to reduce PV oscillations. However, most of them cause excessive valve movements and many of them require prior process knowledge. It is observed that the four-move methods and the novel Stiction compensation methods are the best among them. In my FYP, 3 recent compensation methods will be simulated in different case studies and make the comparison among them apple to apple in order to observe the performance of each method. Firstly, we will share about the mechanism of four-move methods. When the process output OP is increasing close to its peaks, the controller is switched into open-loop mode at time 0 and OP is set to maximum. Then, after a certain time interval, OP is enforced to minimum. The compensating signal UK is not added to the controller output, but the valve input U is switched between these two signals. When subsequent oscillations are detected, the compensator is activated by using the move in OP equations. Once the steady state is reached, if somehow PV diverges and the error passes the predefined threshold limits or the set point change is detected, the loop is switched back to the standard PID controller. Then, compensations is renewed and remove again the oscillations. The extreme oscillations of OP are recomputed each time to get the desired steady-state valve positions. With these methods, no aggressive valve movement will be created when reducing the valve oscillations since the compensator pulse will not be added to the valve continuously. Next is come to the variable amplitude pulse method. This method is adding the pulse with varying amplitude to the controller output in order to overcome the Stictions. When the error becomes smaller than the specific limit, the compensations will stop and remains at the standby mode. The compensations will restart once the error is again exceeding the limit. The more detailed mechanism will be explained in the next slide. K here indicates a sample time. R K is a ramp signal and it was set to 0.5 and end with 0.2. The slope is given by delta, tau is the approximate value of time constant of the control loop, and Ts is the sampling interval of the loop. the RAM RK may adjust the amplitude of the pulse so that they are large enough to overcome the stictions, but at the same time it's not too large to cause the large error and the warp interval. The pulse are reduced according to the new value of RK and UVK that is applied to the warp. UVK is the sum of PI signal and compensating signal. If absolute error EK is less than the specific limit, the process will be counted, and after certain counting, which is more than the NE, the pulse will be stopped. In order to stop the pulse, the amplitude of the RAM, which is RK, will be set to 0, and eta symbol, which represents the deadband for the integral actions of PI controller, will be set to delta. This action is required to prevent the integral actions of the controller to bring the oscillations back. If the error below here is greater than the limits, the amplitude of the pulse will be remained at 0.5 and setting the deadband integral actions eta to 0. Lastly, we will discuss about the novel compensation methods. The compensator will be receive two signals which are control error signal and the control output signal. If the warp stem becomes stuck at the fixed positions, the error signal keeps increasing. When the error signal reaches the predefined limit, the pulse generator inside the compensator is activated and it will generate a pre-designed pulse. In this compensator, two outputs will be generated here, which are compensator output with pulse and reduced control actions. Two input signals will enter the compensator. The system will check whether the error signal is greater than the predefined threshold epsilon. If the control error is less than the epsilon, the TP, which is the start counting time period, will be 0 and proceed to the output with the equation dividing by the detuning parameters. Else, if the control error is greater than the predefined error limit, it means that the warp stem starts at the fixed positions. After that, if TP is greater than the specific time limit, means that the warp still remains stuck at the fixed positions. It may send the signal to the pulse generator where the pulse will be added to the output signal. If TP is smaller than TG, means that the warp can already move and functions. Then it will return and proceed with the normal output signal. Hence, basically this is how the compensator works. These compensator methods require the usage of simple pulse generator, and the detuning parameters is the only parameters need to be specified each time depending on the controller and the process. Let's move into the methodology. This is the Gantt chart of my FYP showing the flowing and the dates of the whole project. It has been distributed into three parts, which are the research study that has been covered in FYP1, modeling where will be start soon, and the assessment. In order to do the modeling, firstly, we will define the scopes of the simulation where we have narrowed down the recent 3 PID-based compensation methods. Then, we will define the case study since we need to set the same parameter for all three different methods in order to compare apple to apple. After that, we will run the simulation on those three methods and compare the results of response curve, whether there is any oscillations on the output, and so on. If the result is not satisfactory, we may repeat simulations. Once the result is good enough for the comparisons, we may start to identify their weaknesses and determine which is the most ideal methods. The modifications will be done on the most ideal methods by modifying its algorithm. Next, we will run the simulation on the modified methods and compare it with the before modified versions. If the result is not satisfactory, we may continue to modify it. Finally, it will be applied on the pilot plant or do the benchmark simulation study. As mentioned just now, we will set 4 different case studies for the simulation purposes. The first method is the well-tuned controller, which represents a good conditions of the control valve. Second case study will be putting the excessive integral actions on it. The excessive integral actions may causing the dispersions of output data, and third, the R-square value is slightly lower than the well-tuned controller. Other than that, we will add external oscillatory disturbance with the sine signal and stictions to the control valve. Therefore, it may able to test the compensation methods whether they can identify which has the presence of stictions even though both cases has large oscillations. The R-square and RNC values here indicates the nonlinearities of output data from each case study. If R-square is less than 0.8 and RNC is larger than 1, it shows to have a stictions in the control valve. This is the simulating model which can change to each case study alternatively. We can set to have excessive integral actions, add the sign disturbance, or add the stictions to the model. To summarize what will be covered in my FYP, according to the literature review, the novel Stiction compensation methods is the most ideal model among the others, since it can reduce the oscillations, not create any excessive wave movement, and not require prior knowledge to specify and determine any parameters. Hence, the modifications can be done on this method by improving the detuning parameters in order to enhance the feasibility of novel Stiction compensation methods. That's all from me. Thank you.